This is our fourth lecture video on kinetics, and I wanted to start by looking at what you're going to be doing in lab because it applies so much to what we're talking about in lecture. So in lab, you're going to be looking at three different variables which affect the rate of the reaction. In one part, you're going to be looking at how concentration affects the reaction rates, and in another section, you're going to be looking at how temperature affects the rate of the reaction, and we're also going to be looking at how a catalyst affects a reaction rate. So in this lab, you will be determining the orders of a reaction, the rate constant, and the energy of activation. So the reaction that we're going to be looking at is the reaction of iodide reacting with bromate and acid to produce iodine, bromide, and water. So the rate law expression for this reaction is the rate equals the rate constant times the I minus concentration raised to some power, the bromate concentration raised to some power, and the proton concentration raised to some power. We're going to actually be determining those orders of the reaction, so the M value, the N value, and the P value. But we're not going to be directly measuring the rate of the reaction. Instead, we will be recording the time it takes to consume a fixed amount of sodium thiosulfate. Basically, the analogy of running a race, the sodium thiosulfate represents the distance, and we will record the time it takes for the reaction to run the race. Thus, we'll be determining the relative reaction rates. We won't actually be measuring the reaction rates themselves, but we're going to be comparing how long it takes the reaction to complete by changing the initial concentrations. So the sodium thiosulfate will be our limiting reagent, and that's going to determine how long the reaction is going to occur. So the molecular iodine that's produced from equation 1 will almost instantaneously be consumed by thiosulfate ions as described in equation 3. In equation 1, we're looking at the iodine, the bromate, and the acid coming together to make the I2, the bromide, and the water. And then the iodine that's produced, the I2 that's produced, is going to immediately react with the thiosulfate, so the S2O3 2-. And then once all the thiosulfate ions are consumed, then the I2 molecules would then react with a starch that's added to the solution to make a blue-black complex. And when you see the blue-black complex, this tells us that all the thiosulfate has been reacted, and this signals us when to stop the time measurement. All the reactions are going to run the same distance. They're all going to use up the same amount of thiosulfate. It's just we're going to time to see how long each reaction takes place to reach that same point. And that change in color is going to help us know. So this will be representative of some of the data that you'll actually collect. So you'll determine your initial concentrations, your I minus, your bromate, and your acid concentration. And you've got different concentrations or different trials that you'll do with different concentrations. And the temperature needs to be the same for all of these. And you'll measure the time it takes for the reaction to occur. And we're going to take 1,000 divided by that time to get the relative rates. Once we have our rates of the reaction, then we can start setting up our ratio like we looked at in our previous video lecture, and we can determine the orders of the reaction with respect to each reactant. Now also in that lab, we're going to be measuring the energy of activation. So remember, this is our Arrhenius equation where K equals A times E raised to the negative E sub A over RT. Algebraically, the Arrhenius equation can be arranged in the following form. So basically what we've done is we've taken the natural log of both sides. So I took the natural log of K, so the ln of K equals the ln of A, and when I take the ln of both sides and these are multiplied, this would be the same thing as saying the ln of A plus the ln of this term. And since we're taking the ln of the natural number E, that disappears, and so we just get the negative E sub A over RT. And when it's arranged like this should look familiar to you because this should look like an equation for a line if we plot the ln of K versus the inverse temperature. So in this case, the ln of K would be on our y-axis and inverse temperature would be on our x-axis. And from the slope of the line, we can get the energy of activation. So if we take our slope, multiply it by r, and by -1, we can get the energy of activation. We can also get the frequency factor from the y-intercept. Now alternatively, you can replace the ln of k with the ln of the relative rate and use this on the graph to determine E sub A. And this is actually what we're going to be doing in lab. We're going to be plotting the ln of the relative rate versus the inverse temperature. And this gives you an idea of some of the representative data that you'll be collecting. So from this equation of the line, so the slope is minus 2,709. If we multiplied this slope by the gas constant and by -1, we can get the energy of activation for this reaction. Now sometimes when we're trying to figure out the energy of activation, we don't always have enough data points to do a graph, or graphing may be too long. We can do an approximation if we just have 2 data points. But experimentally, it's best to plot the data with as many data points as possible so that you can get a best fit line. But sometimes you don't always have that much information, and sometimes you need to do a 2-point version of the Arrhenius equation. So this is how we're going to get the 2-point form of the Arrhenius equation. We're going to derive it. So we've got 2 different samples. We've got one at one temperature, T1, and the other at another temperature. And remember, changing the temperature changes the rate of the reaction. So this is why we have one K value and another K value. Now the frequency value, the A value here, is a constant. It's going to be the same in both reactions. So what I've done here is I've solved both sides for A and set them equal to each other. Now I've just isolated the K values on one side. So I've divided both sides by the K2, and then I've taken this denominator here, multiplied both sides, and I moved it to the top here. So this gives me this equation here. Now I'm going to take the ln of both sides. So the ln of the K1 over K2 equals the ln of this entire function. Well, the ln of this numerator and denominator, I can separate these out by saying the ln of the numerator minus the ln of the denominator. Then what I'm going to do, and since I've got the ln of E, that disappears, so now I just have the negative E of A over RT1 equals the negative E of A over RT2. Now I'm factoring out the energy of activation and the gas constant, because remember, the whole point of doing this Arrhenius equation is so that I can find the energy of activation. So now that I've factored this out, I'm going to get rid of the -1. So now notice that the position of the T1 minus the T2 here, we've just reversed these when I got rid of the -1 in front. So this is the 2-point form of the Arrhenius equation. And you only use this when you only have 2 data points, the temperature and the rate constant, when you're trying to find the energy of activation. So this ends our 4th video, and in the next video we'll be looking at reaction mechanisms and catalyst to finish out our lectures on kinetics.